For this month's practical chemistry video, we are looking at percentage error calculations, how we do them, what we mean by the word uncertainty, and how we use it in different practical contexts. So first of all, we need to decide what we mean when we say uncertainty. So uncertainty is really just, how different our results might be from each other and also how different they might be from the real result. And uncertainty can come from many different places. So it can come from experimental observations, limitations of people really. So for example, we might have a different idea when we look at colours about what colour something is on a pH chart, or somebody might have a different idea about, for example, when a cross disappears. We're doing a classic rates experiment. But more normally, when we're talking about uncertainty, particularly when we get exam questions about it, we're talking about the limitations of the equipment we use. No equipment is perfect. There has got to be sort of a maximum level of certainty that we can read to, and so that's what we mean. We mean that what's the sort of size of the gap between readings that we could expect as our uncertainty value. So a lot of the time uncertainty has a number or value assigned to it, and it depends on the equipment as to where that value comes from. And there were sort of three main examples that we should be familiar with. So one of them is a equipment with an analog scale, a scale that we're reading off from some sort of lines, and we're reading off the lines, like a mercury or alcohol thermometer. So for this, the uncertainty is generally due to how closely we can read it. So it's the resolution of the equipment. So if I look at this thermometer reads in 1 degree divisions. So that is the smallest division between the lines is 1 degree. So the uncertainty, well, I can't say that I can only read to a whole degree. I could tell whether the thermometer line is exactly on one of those divisions or whether it's kind of halfway up, but I can't really see anything more clearly than that because the lines are too close together and too small. And so what we can say is that the uncertainty is plus or minus half the smallest division there is. And so it's plus or minus 0.5 degrees C is as accurate as I can be. So at the moment, how I would record that is I can see that it is 24 degrees. So I would write it as 24.0 degrees, and it's plus or minus 0.5 degrees C. That's my uncertainty. Even more common than that is the classic burette used in titrations. So reading down this burette to get the volume, I can see that it is 38.1 centimetres cubed. Now the divisions are 1 centimetre cubed, which actually means, just like the thermometer, I can read halfway between those on a burette, which means that I know that it's somewhere between 38.05 and 38.15. Like, I know it's not those two, it's in between them. So actually the accuracy here is half again. So 0.1 centimetre cubed, is the division. Half the division is the uncertainty, in which case I should put a 0 there to show that I'm being more accurate, and 0.05 centimetres cubed. Okay, we'll talk about recording in a moment as well, and how it relates to results tables. That's things that there are divisions on, but I mean, measuring cylinder, we can sort of do the same thing. Measuring cylinder reads 1 centimetre cubed in the division, so we can pretty much say it's plus or minus 0.5, although if it's just a sort of cheap plastic measuring cylinder, it actually might be a little bit less accurate than that. When it comes to wanting really accurate apparatus for measuring, what would be ideal is if we only had one division, and then the uncertainty is not about the space between and whether we can read it, it is simply about how accurate that line itself is. And so volumetric apparatus, volumetric pipettes and flasks often just have that one line on them. And so a typical glass volumetric pipette will have a uncertainty value of only plus or minus 0.05 centimeters cubed. To be honest, you're more likely to be out by more than that because of just your own ability of using the pipette and reading off it and everything else. Okay, finally, we have digital equipment. So rather than analog, gives us a digital readout of the exact number. We don't need to work out where something lies. And for a digital reading, the uncertainty is half of the smallest number you can read. So actually it's really similar to the previous one. So if I had, for example, a 2 decimal place balance like this one here, well, the smallest number that I can possibly read is 0.01 grams on this balance, and so the uncertainty is going to be half that. It can be 0.005 grams higher, or it can be 0.005 grams lower. Any more or less than that and it would change the reading, and that's what we mean. So therefore, if I had a 3 decimal place balance, the uncertainty is plus or minus 0.000, 3 decimal places, and then a 5 after that, grams. Okay, there are not many other digital pieces of equipment that we commonly use in chemistry, but the same rules would apply. We did say we would talk about how this comes to recording results. It's really important that we reflect the accuracy and the precision of our equipment and the resolution of our equipment in all of our readings, and that they are consistent. So this is a terrible looking titration table, and we're going to fix it so that every single reading is plus or minus 0.05 centimeters cubed, which means that it's not 10.1, because I know that actually that reading is not just between 10 and 10.2, it's between 10.05 and 10.15. So that's why we add the extra zeros. Even on my 00, that's one where people really forget to do it. I'm going to make sure that they're all to do decimal places, but notice that the second decimal place is just 0 or 5. I can't get any more accurate than that. Similarly, if I was going to do temperature, using that thermometer we just talked about, notice they're all to 1 decimal place, and the second decimal place is a 0 or a 5, because we can only read to the nearest half a degree. And then with my balance, we're just making sure what happens is when we do a difference in readings, so for example, here we've done a mass of empty and a mass of crucible, and after heating has just turned out to be 27.00. We've just got to make sure that we record those zeros and don't get them lost along the way. Okay, let's finally get on to calculating percentage error. So it's a pretty relatively straightforward equation. Percentage error is going to be the number of readings you take, and we'll talk about when there is more than one reading in a minute, times by the uncertainty value. So that's my plus or minus value, either that I get from the resolution, the scale that I'm reading off, or I'm told it. For example, I might be told the uncertainty in a pipette, or again, I get it from the resolution of a digital balance where I go to half the smallest reading. So that's my plus or minus value. And then I'm going to divide it by the value of the reading, and we will look at what we mean by that in some examples. And it's a percentage, so I'm going to times it by 100. So let's apply this to a really simple example. I'm going to measure out 25 centimeter cubed of a solution, and I've got a choice of either measuring it in a measuring cylinder or in a volumetric pipette. So remember, the measuring cylinder has a uncertainty of plus or minus 0.5. I'm only going to read off the measuring cylinder like one volume. I'm going to just get it to 25 centimetre cubed and read it off. So in terms of number of readings, for a measuring cylinder, I'm only making one reading. I'm just looking at where does my solution get to the 25 centimetre cubed line. So there is one reading. The percentage error is therefore going to be the uncertainty, which is 0.5 times by 1, if you like, divided by 25 times by 100, and that equals 2%, which doesn't seem particularly big. But remember our volumetric pipette for measuring at 25 centimetre cubed, and the uncertainty in a volumetric pipette, which I'm also only going to read one line on. So I'm only going to make the reading of when does the solution hit the 25 line, and it's going to be 0.05 over 25, the same reading, times 100, and so it's going to be 10 times less at just 0.2%, which explains why we use volumetric pipettes for things that we need to be very accurate, like titrations. Okay. That was an example where we only take one reading. Where would we take more than one? More than one, incidentally, almost always, can't think of any other examples, it's usually just 2. So it's never like, 25. First of all, what we want to be careful of, we're going to use burette readings as an example. Quite often in a titration experiment, we would do a number of repeats. Number of readings does not mean how many times I repeat the experiment. The purpose of reading the experiment, of repeating, is to get concordant results. So when it comes to the value of the reading, it's going to be the results that I use, that I put in my calculation to find out whatever I'm trying to find out in the titration, concentration, whatever. So first of all, concordant means either 0.1 centimetre cubed or 0.2 centimetre cubed. It sort of depends on exam boards and things. That means that these two are my concordant results. And notice also that when we say the reading that I use, the reading that I use is not 29.25, 38.7. It's none of those numbers above. It's the final volume added that I'm going to use in my calculation, because that's what's going to affect my experiment. So that's what I'm interested in. What's the percentage uncertainty or percentage error in that reading? So I'm going to take an average, 9.40 plus 9.45 divided by 2 gets me 9.425 centimetre cubed. So that is my actual reading. With a burette, remember that we said that each reading, the uncertainty value, because of how we can read the burette, was plus or minus 0.05 centimetre cubed, because the scale goes up in 0.1 and we can read halfway between the lines. But I'm using a burette twice. We can see that really obviously from the table. There is an initial reading and a final reading, and then I take the difference. So what I need to do when I calculate my percentage error is I'm going to do 2 times 0.05 divided by the value that I'm using, so my average result, times by 100, and that gives me a percentage error of 1.06%. So other examples of where we would take 2 readings would be anything where we have a change that we're recording. So a change in temperature, we have to take an initial reading and a final reading. So there are 2 errors there, the 2 sources of error, 2 uncertainty values to put in. And then a change in mass, anytime we use mass, we zero the balance and then we measure something, or we measure something like a solid in a weighing boat, and then we measure the weighing boat again. So usually when I record mass, there are also 2 readings, especially if I'm doing something like alcohol spirit burner and I'm looking at the change in mass after the experiment. So lastly, we're just going to look at how you might reduce percentage error. And the first thing that students tend to jump on if they're asked, how would you reduce the percentage error, is they think about the equipment, which is fine, but you need to use the right wording and be specific about it. So absolutely not going to get any marks for saying use more accurate equipment. We need to be specific about what equipment and more precise or higher resolution, not more accurate, because actually it's not necessarily, the two things don't tend to always correlate. So for example, you could say use a more precise thermometer. That would be a good way to reduce, well, it would reduce percentage error. It wouldn't necessarily increase accuracy, because actually digital thermometers are not that great. Or if, for example, we used a 2 dp balance, we could say use a 3 dp balance instead of 2 dp. So we're being very clear about what we're changing about the equipment. Another example, of course, if we're measuring volume, could be use a volumetric pipette instead of a measuring cylinder. Very clear what we're changing, and we're doing it because it has a small uncertainty value. But just be careful though about what the question's asking, because lower uncertainty or higher resolution, more decimal places, doesn't automatically equal anything better or higher accuracy about your result. There are some experiments that are just quite flawed. For example, anything where we're measuring enthalpy changes, there's always going to be a lot of heat loss, and that's going to be the major source of error. So if I'm heating up some water with a burning alcohol and I decide to use a pipette to measure the volume of water instead of a measuring cylinder, it's really not going to make a huge deal of difference to my accuracy of my result, because my accuracy of result is mainly ruined by the fact that there's a load of heat loss. So actually there's other things I can do in that experiment, like using a lid or insulating it more, that would help improve accuracy. So this is only to be used if it's specifically asking you about reducing percentage error. Finally, there is one other way that we can think about reducing percentage error. So previously we've been looking at making this value smaller. So if I change, for example, from a measuring cylinder to a pipette, then I'm reducing the uncertainty in the reading. The other thing I can think about is there a way that I could make the bottom of this fraction larger? Is there a way I could increase the value of the reading that I record? Now you might be thinking, well, how do I do that? Because it's like, that's my dependent variable. That's the thing that I'm measuring in the experiment. So how on earth would I make that bigger? Well, you can change some of the conditions that you're using, because you've got some control over what you choose. Let's take this example. We have a solution in the burette, and this volume is relatively small, so less than 10 centimeters cubed. A burette holds like 50, so that's quite a small volume. Well, how can we make that smaller? It depends on the concentration of the solution in the burette and the concentration in the flask, and also like how many moles there are of each. Depends on the concentration and volume. So if the thing in the burette is the thing that I know about, which it quite often is, i.e. the thing that I know the concentration of, like some sodium hydroxide, at the moment it's requiring quite a small volume, which suggests that that sodium hydroxide is quite concentrated. So what I could do is use a more dilute solution in the burette. If that's the unknown thing, obviously I can't change the concentration of it if I don't know the concentration. So the other option is I could use more concentrated solution in the flask. So if that was my known solution, I could change the concentration of that, make it more concentrated, or a bigger volume in the flask. So if, for example, I was only putting in 10 centimeter cubed in a flask, could I put 25 centimeter cubed in? The bigger volume would require more moles of the thing in the burette, that would reduce the percentage error. It's not necessarily going to make my experiment better. If I've only made 100 centimetre cubed of solution, I don't want to waste 25 of it in one titration because I might not have time for repeats or enough for repeats. But that's one thing to consider if you're getting those weird scratchy head questions about suggestions on reducing percentage error without changing the equipment. Alternatively, for example, a temperature change. So temperature change in a chemical reaction requires us chucking in two things together, maybe an acid and an alkali, or maybe I want to add some magnesium to some copper sulfate, whatever, I'm measuring a temperature change. Now if the temperature change is really small, like 2 degrees, the percentage error in that from a normal thermometer is going to be really large. So what we can do, one thing we can't do is add a bigger volume of water or solution, because if we do that, we're heating up more water and it will take more energy. So again, this is a situation where we would use a more concentrated solution. So we don't want to increase the volume in this case. Increasing the volume will just give us more to heat, so the temperature won't go up as much. But if we use a more concentrated solution of whatever we're adding together, then we should get a bigger enthalpy change because we're using more moles altogether.